Yeah.
I had to configure the BIOS.
There's one you gotta figure out. Yeah, you can
No, I had to configure the BIOS to change incoming connections. Yeah, isn't that weird? For what?
Still login times. System login was like timing out. I had to run a debug process. But so by restarting, it's still good.
For 16, like, why not this is
I restarted the ding.
Oh, okay. You're talking about Super? Okay.
Sorry guys, my computer like crashed. It might just crash if I do this again, but it crashed a second ago. So I have to pull up everything that I wanted to have prepared for you guys. All right, start for the day. So it seemed like everything went okay with the 2 days I was gone. I guess it was okay. You could follow the lecture over video. It was okay. And the lab, I guess it went a little bit slower than I thought, but it's okay. So what I want to do today is, shoot, that's the wrong lecture. No, I guess I can change the number. Okay, maybe don't shoot for. I just forgot to change the title. So we were slated for starting to linear algebra today. And actually, there's not much about linear algebra that I want to tell you guys. I just, because I don't know how many of you have had linear algebra, and I don't know how many of you have practiced just coding up things with matrices. I just want to do a couple of those things in front of you. It's very simple, basic stuff. Most of you guys will be bored with it, I hope. But just because if you haven't seen it, then you're going to struggle with it, so I want to do that. So the goal today is, if I can change the slides. So I want to talk about the lab. I'll bring that up, and the homework. I'll finish the deep learning software stuff that I was talking about. There's a couple of slides I didn't do last time, so I'm just going to go there. I'll quickly review what I said and then go there. And I'll pause for questions in case there were some questions, whatever. And then I'll go into linear algebra stuff. And then I have some Python notebooks just as examples. I'm going to do some coding in front of you guys. Okay? We'll see how much of that we get done. My goal today is to get to linear algebra. I wanted to have you guys actually do a lab on NumPy on Wednesday, but you guys weren't quite there, and I wanted to give lecture. So I'll give that lab to you. I'll give it to you Monday. And I think the way this is going to end up is that the homework and the labs are essentially the same thing. I'm effectively, probably what's going to happen for most of the homeworks is you're going to start them here in the lab, because I want to make sure you guys are all understanding what's going on and get started and everything, and then you have things that you have to finish as homework. And then, so that's probably what's going to happen, just like what happened with the first lab. So on Monday, I may take some time, a little bit of time to introduce that homework, NumPy and that homework, and so it might be a little bit lab-wise, I really recommend you guys bring your laptops every single time you come. Because it may be that I want to say, hey, it's the last 10 minutes, let's make sure everybody can pull this up and everybody understands this and it's all working for them before you leave, okay? So I want everybody to try to bring your laptops to class. Okay, so let's talk. So we were talking about deep learning software. So I went through this stuff with you guys last time. We store data in the tensors. Was this all clear to people? With the, we just they're basically n-dimensional arrays. We fill with numbers and put our data in there. Typically, the first index is that when we're doing things, we're training things, where we're giving examples, right? Example pictures or example data. And so I might have 1,000 example pictures, or typically more like 1,000,000 example pictures. The first index, so if I say x, 0 would be the first picture, x1 would be the second picture, and so on. And then if it's just, let's say it's pictures, then pictures are two-dimensional objects, right? So the next two, because they have the x and y coordinate, right? What a picture is in terms of matrix would be, this x, this y, this is the color that's there, right? That's what that represents. So the shape of something like a picture would be, if I look at the shape. So if I look at the shape, so I'm doing this notation is really coming from NumPy. But if you ask the x for a shape and it's pictures, there'll be some number, n, like 1,000 or 1,000,000, how many you have. And then there'll be sort of, I'll say nx, ny, right? Which would be the number of pixels in x direction, number of pixels in the y direction, right? So if I ask for x of 1, it'll give me back and ask for the shape of that, will be whatever this nx and ny are, right? For example. But here in this data is sort of one-dimensional, right? So this whole thing is only two-dimensional because it is not pixels. It's just values of some parameters like age and whatever. Okay. Right. I think I did an okay job talking about this. We'll come back to that. This formulation of the machine learning problem. So we define a data set, right? So you have your training data set, a test data set, and then some data set that you want to actually, the whole reason you did this is because you don't know the answer somewhere, so you have a data set you can apply it to. Okay, some unlabeled data set, let's say. What you want to do is find a function that goes from the input to the output, right? And when you do that, what it'll give you is a prediction. That prediction isn't the truth, it's the best that it could do if you train this thing, right? It's not necessarily the truth. And what you do when you train is that you take the prediction and compare it to the actual truth for the training set and try to change the whatever function this is so that they can become closer and closer to each other. And the way that you calculate that depends on the problem that you want to do. But when I say you compare. Now, a basic comparison could be you just look at the, y is a bunch of values, and you just take the difference between the predicted values from what you want the values to be, and then you probably should add them up in quadrature. So this is what this is. This is f of x, that's given the input, given some parameters, what f is the prediction, minus the training. This tells me that I should use bigger fonts. Minus the training squared could be a cost function. Okay? This is taking the difference between them, and because I don't want the differences to be, I want to add them up, without the difference to be positive. I don't want that if I overshot one and undershot another one, I'll cancel that effect up. That's why I score the whole thing. Okay. And then, right, so you have your data set, you have some goal, something you want to do, you do your training, then you do some validation, which is you take some of the data set that you didn't you didn't use in the training, but you do still know the answer, and you test how good it is at getting the answer. So for a classification problem, and this is what I'm trying to explain here, when I run the, let's say, neural network on pictures of cats and dogs, and I say 0 is a cat and 1 is a dog, when I'm training, when I give it a picture, it's not going to give me exactly 0 or 1. It's going to give me some number between 0 and 1. It's up to me to decide what the threshold is where I decide that this is going to be a cat or dog. Okay? And so that we'll talk about that process and how to do that and what that means. But I just want you to understand that point. And a way that you can set some criteria. You can say, oh, when it's greater than 1/2, let's say it's dogs, below 1/2 is cats. That's my criteria. And then using that criteria, you can then see how well, how your performance is. And what you do is you know the answer. So you take the pictures of only dogs and give it to it and see how often does it do the real dogs be identified as dogs or as cats. You do the same thing with cats. So you get this, what's called a confusion matrix, which is how often, one category thing gets misidentified as the other thing or correctly identified. Okay? So we will calculate those things. We will do this more formally, but I just want you to be, get these ideas in your head. Okay? So that was that part.
I have a question.
Yeah, please.
How we can get the prediction function?
The prediction function. This function.
Yeah.
So that's actually the next step, right? So the function it could be anything, right? So I said it could be heuristic, right? It could be if this then that kind of thing. But it's for us, it's going to be a neural network. So let me just show it to you in a second, right? So what you actually do is you take the cost function, you minimize the cost function with respect to the parameters of the neural network. This parameter is A, or to look at the alpha. Alpha. That's how you get it. But that's what I'm explaining in the next few steps, right? So yeah, so this is then this is a formulation of a neural network. Let me come back to this because we're going to do linear algebra, but in a second. But this is just a simple linear algebra equation, right? This is x is the inputs times a matrix W plus a vector B of this, which is the same dimensions as x. So this is and well, when we get there, I'll show you why this is the right thing. And then you take some function that looks like this, which simulates the activation of a neuron in some way, or approximates it, of that whole thing. That's basically one layer of a neural network. Okay, that's what that says. So we talked about this last time. And so that's the function, right? And what I want to do is I want to minimize. So I'm just redefining this by just hiding away these things. I'm just going this is a cost function, which is a function of these parameters, like you're minimizing this thing for. So this is my cost function. And what I want to do is minimize this cost function. And that I do through gradient descent, which, let's say, with two-dimensional, is basically like walking around a topographical map and walking around the gradient, which I explained last time, and you guys should probably be familiar with. Okay? And then, so the steps are, here's where I am in that space, right? This is my x and y coordinate in that space, whatever these parameters are. I calculate the gradient at that particular point. This should be an I here. At that given point, and I take a step in the opposite direction of that gradient, right? And that gives me the next set of parameters, and I'll just keep on doing that. That's pretty much what training is. All right, so this is what I want to slow down on. So that was the basically formulation of what we do in mathematics, what has to happen, which is you got a bunch of data that's stored in tensors and high-dimensional tensors. You're going to do some very basic linear algebra and take some basic functions of it, and then you write down some cost function, right? So you write the neural network as some expression, and then you write a cost function using that expression, and then you minimize that cost function with respect to the parameters, and that's your training. So when you then are going to do that in practice, what do you need to do? Let's say I have a problem, I've got some data, what do I need to do? The first step is I usually have to prepare the data. The data may not be in the right format, maybe I have to organize it a little bit, maybe I have to clip it, do something to it, or just change it into, just somehow do whatever, my data might not be the right, might be in comma separated files, or might be in some other format. I'll have to convert it into tensors, okay? So that's what I mean, that's the first step. The second step is you want to build your model, what you want to do. So you want to write down that expression of that neural network, okay? So that's our models are neural networks, right? Then, if you've done that, you want to define what cost function, or sometimes it's called loss function, you want to use, right? And you may choose different loss functions depending on whatever you want to do, okay? And then you want the training, which is basically calculating the cost function, with this model on the subset of the data you're going to use for training, right, and minimizing it, which I just described. That's what you need to do. And then you assess the performance. You get this fraction of the sample that you had that you put aside for testing. You assess your performance. And then you basically repeat lots of experiments. You go and say, well, that model, maybe I can tweak the model a little bit. I might change the model and try again. And you do this many, many times, and you get the best model you think that you can get. Okay? So that's what so people who are doing deep neural network training, and you guys, you're going to have to go through the steps. So the toolkits that have to be out there have to make that happen. Okay? And there are two, I would say, classes of toolkits are out there, sort of standard toolkits. One are very much like actually the frameworks in our high-energy physics, but they're basically, they are a bunch of functions that are written in C++, right? And what you do is you just, using some sort of a scripting language, kind of like Python, but doesn't have to be like that, you'll go through and you pull them all together. And you say, basically, you construct your network by just saying, oh, give me this layer and that layer and that layer, and everything's implemented and just allows you to construct your model by picking and choosing different bits and pieces of things and putting it together, and you say train, and it does the training and all that stuff, okay? And the point here is that, in some sense, most of the calculation of the things you want to do here is written in C++ code, and all you're going to be really doing is configuring this thing to run. And there's packages, and you'll see, so the two big ones are Torch and Caffe, which are sort of this way. You don't really, particularly in Caffe, you don't give Caffe some code or something. What you do is you give it a description of what the network should be, and it makes a network for you and trains it and all that stuff, okay? That's different to something like Theano and TensorFlow. Theano and TensorFlow are actually not fundamentally deep learning sort of tools. What they are computation tools, okay? And I explained that to you before what Theano was. It was a way of doing sort of matrix operations by getting it compiled and running on GPUs as fast as you possibly can, okay? So it lets you, what Theano does, and TensorFlow is similar, what it allows you to do any computation you want to do very, very quickly. And so in Theano, what you actually do is if you want to do one layer of a neural network, what you do is you write down the expression of wx plus b and then some activation function. And what it does is that takes that expression and builds a directed acyclic graph, what this is, which says you take w and x, you do matrix multiply, then you do add to b, and then you take that function, which is this is your activation function. Okay? That's okay. It constructs that graph. Now this is one layer. Multiple layers with a more complicated graph, and you can imagine having a very, very complicated graph. Okay? And okay, so that's what it does. So if you want to use those things directly, you effectively have to write the expressions yourself. That's different than here, where that stuff is, all this is coded up in one piece of the code, and you just say, I want this function, right? I want this type of layer. It's different than actually writing the expression for the layer, okay? So that might seem that it makes things more difficult, and it does, because then you have to write everything by scratch. So in order to be able to not have to do that, they've built a very lightweight framework in Python on top of these packages. So one of such framework is called Keras. And what Keras does for you is write down this expression for you. So in the end, the way you interact with this and that are very similar in that you say, to this one you would say, I want this layer and this layer and this layer. You say the same thing to Keras, I want this layer and this layer and this layer. What Keras does is write down the mathematical expression, and then takes that mathematical expression, gives it to Theano to create this directed acyclic graph and optimize and create code and basically compute that expression as fast as possible. Okay? And now, I just now talked about computing that expression, but it's not that you just want to compute that expression. What you need to do is do that many, many times and also calculate the derivative of that, right? That's what the thing in training is going to be. You have to evaluate the expression, you have to evaluate the derivative of that thing, right? Take a step and keep on doing that, right? Now, you could take the derivatives actually numerically. How do you take the numerical derivative of the function f of x? If I wanted to figure out if I have a function f of x and I want to take the derivative, what I'll just do is evaluate it here and evaluate it x plus some dx. And then basically it's the definition of a derivative, basically, right? That's my derivative, right? I take the function, subtract from it some step from it, divided by the step that I took. That's my derivative, right? So you can numerically calculate derivatives, but calculating derivatives numerically ends up being more expensive because I'll have to calculate the function once here, and typically I'll have to get this derivative good. I have to do this a couple of times to get a nice evaluation of the derivative. Okay? And what I'll have to do also is I'll have to do if I have a multi-dimensional function, I'll have to do this call for every single variable, right? So I have to individually so I have to do this computation as many times as it's got variables. Okay? And you can do that, but it ends up being slower. Another way to do it is that instead of doing this, you can just actually have the functional form of the derivative, right? And so that's what these frameworks, most of them do now, but it wasn't necessarily there in the beginning. To get the functional form of that derivative, because Theano and TensorFlow keep track of this mathematical expression, they can actually apply simple rules and symbolically figure out what the derivative expression would be. Okay? And that's what these tools would do. This is the nicety of them. You write this thing, and it's actually very complicated because what you're truly doing is, if you think about it, this is a matrix of a bunch of numbers, right? And so you have to, and so these parameters, each one of these parameters could be a element of this matrix. It's a very complicated thing to do by hand. If you want to do it yourself, this thing will go and calculate the derivative with respect to every single parameter for you and give you that expression for you. Okay? And so that's just one thing you have to calculate instead of having to do it numerically. And so that's one of the benefits of things. And it used to be, and things got different. This was the first beginning versions of these codes where the big ones were Torch and Theano, and they're both very performant. And Torch was more hand-written and more sort of optimized by hand. Theano generates code, more general, whatever. But Theano would beat Torch originally because it did this thing symbolically, right? And it was less effort to write in that sense. But eventually they optimized this, and now there's more parity. Okay? And I think there's symbolic derivatives now to which I don't know. Okay. Okay. So those are the tools. And so TensorFlow and Theano are similar in the sense that they both will create directed acyclic graphs. The difference is that Theano goes off and then generates code, compiles it, and gives you back to the function. Whereas TensorFlow, it already has all these primitives implemented, so it doesn't generate code. It just calls them in the right order and pipes the data from one into the other. So it's slightly different. Okay. And TensorFlow is a product that came out of Google about a year and a few months ago, and because it's out of Google and it seems like something that's being long-term supported, a lot of the community has moved to use that. And actually, a lot of people like us were originally using Keras with the Theano backend. Keras could generate, have either Theano or TensorFlow as a backend. We are now, a lot of us, transitioning from this to that, and just flipping a switch, basically, at the back end. And pretty much more or less everything works the same. Okay. There's one other thing I was going to say. So the other advantage here is that, so in Theano and TensorFlow, if I wanted to change something, if I got some idea, I got a new cost function I want to write. It's easier to do it here because it's building a mathematical expression, so I can modify the mathematical expression, and the code is generated or the thing is computed otherwise. Whereas over here, it may be a little bit more difficult because I have to go to the place that in the internal code where this thing's computed and change something or implement a new. It's a little bit more complicated. Whereas here, I just can play with a mathematical expression. Here, I'll have to code, basically. So this becomes a better research tool because it's easier to try different ideas out. Okay, and I might try to do something, and it might not be, it might be kind of a crazy thing to calculate. And if I do it here, I write the expression, I write the mathematical expression, the optimization happens afterwards. So the expression will be evaluated optimally. Whereas if I do it here, I have to think about how I'm computing this thing to make sure it's still optimal. Because the optimization, it's just calling this thing. It's not doing any optimization or anything before. Okay. So that's one reason to do this. All right. I think, as I said, the data we store into these NumPy tensors. So one of the things about here is that the computations that we do end up being, about 2 orders of magnitude faster to do on these GPUs. These GPUs, what they are they have lots of little cores, and they can do a lot of things all in parallel. And instead of the CPU doing those things more serially, so doing element by element of the computation, here you break up the problem into 2,000 small pieces, and each one of these small cores ends up doing a little bit of it, and that ends up overall being faster, right? A lot of little slow pieces are faster than one really fast big piece, basically. That's the idea. So there's some and then, but the thing is that the GPUs are right now a distinct device in your computer. So there's a CPU in this memory, and there's a GPU in this memory, and they're connected through the PCI bus. So if you were programming for the GPU, what you really have to do is you prepare the data on the CPU, you ship it over to the GPU, do the computation, ship it back, and then decide what you're going to do with it. And that stuff becomes cumbersome. So these packages, you guys won't have to see this, but these packages handle those things underneath. Okay? But you do pay a cost for that transfer time back and forth. Okay? And sometimes it makes it not worthwhile to do the computation on the GPU because the transfer time dominates over the computation time. In terms of storage, there's something called HDF5, which is a very compact and general storage for storing data, and there's nice interfaces for it, and it has a tensor representation that works like TensorFlow, like NumPy, so you can easily store things in that. Okay. So the last thing to say is that now the kind of operations that we do for neural networks, they've been even more so optimized. So now there's actually, NVIDIA gives us libraries of things that do the computations for neural networks really fast. So most of these packages use those underneath anyway. So in the end now, there's kind of parity between all the packages, because in the end, when you land a GPU, they're all calling the same library. Okay, so it doesn't matter. All right, that's pretty much it. All right, so that's that software. So before I do more, I wanted to go to a lab for a second. So let's go here. So this is a lab I had you guys do. Okay. So your homework for Monday is to go through this, okay? To read through the NumPy one. Because we're going to start on NumPy, and I want you to spend some time doing that. So make sure you do that. And in terms of how so you guys are working on the server, right? So the files are in your home directory of your server. And the way I'm just going to collect your homework is just at a given time, I'm just going to copy what's there. Okay, so your current state. I'll just take a snapshot. Okay, so I did that around noon today. I'm not going to be so strict, and especially in the beginning. Eventually, maybe later on, it'll be important. Okay, but I just want to get an assessment of where you are. So I haven't taken a look yet at where everybody got to, but I hope to be able to do that over the weekend, and then I have an assessment where everybody is. But I encourage you to continue working on it. Yeah.
My homework's in the lab folder. Is that okay?
I took a whole snapshot. If I didn't see it, I'll contact you. I mean, we'll figure it out. Okay.
Right.
Okay. So, but try to keep it in the same folder, because now you know how I'm doing it. Try to keep it in the same place.
Yeah.
Okay. So then the lab, the beginning, I told you how to do random, and then you just made some random things. So this is actually solutions to the lab. Okay. The key of this one, so you were supposed to generate a bunch of random numbers between some range, and all I wanted you to do was just to figure out that if I wanted to, if I have something between 0 and 1, and I want to shift it to be between two arbitrary numbers, just to think about that for a second of how to do that. And so if I want to go between min and max, what I'll have to do is, I'll have to find it, so you can write the formula for this out. But basically, I find the range, and so I take from 0 to 1, what I do is I'll take 0 to 1, and I'm going to say I want to go through this range. I'll multiply it by the size of that range. That's what that is. That stretches out, but then I have to shift it so that it starts at the right place. So that minimum is right. That's what this does. Plus. Okay? So, but you can write down formulas to do that. But that's in general, that's what it is. So that was the whole point. And then if you run this thing, then it'll generate, like in my example, 1,000 numbers between -10 and 10. Okay? And then some basic things. I wanted to see what type this is. So this is, I made a list. So the way this thing works, I mean, I'm going very slowly, but I think some of you haven't understood this yet. So I made a list, an empty list. I figured out what my slope is, and I didn't use it. I don't know And then basically I'll go in a loop and between 0 and n, so because I need n numbers, and so I'll call random, I'll shift a thing, and then I'll append that result into the list. So every time I do this, I get something, and then after the end of this, I've got n things added to the list, and I return that list. Okay. So then I'm just asking, what is the data type? It's telling me it's a list. That's the first thing. What's the length? It's 1,000, right? Length. And then I say if the length is greater than 0, otherwise I get errors. What is the type of the content? So I ask for the first element of this guy, and it tells me, oh, it's a float. Okay. And I can ask for the minimum and maximum, for example. And it was between minus 10 and 10. You can see I'm pretty close to that because I created 1,000 things in between. Pretty straightforward. I want to calculate the mean. So I look at your answer, and your answer was wrong.
Yeah.
And I think it was kind of, I was surprised, but it's a great, but it was like a kind of a common mistake. You just have to make sure that you have the parentheses right. I'm pretty sure yours wasn't right. So basically, the mean, what I want to do is I want to take all the numbers, right? I have 10 numbers. I want to add up the 10 numbers and divide by 10. Okay. And I think the way you wrote it, the interpretation of the parentheses may not, maybe it works out, but I think it.
Okay, I'll check.
So basically, that's what I do. I'll just sum all these guys, right? M equals the sum, and then I take that and divide it by the length of this thing, which is the number of elements, and that'll give me the mean. Pretty straightforward to do. This wasn't meant to be hard. So here, next I'm introducing a little bit of a higher level concept here, which is I want to be able to have sort of functions that take functions as arguments and do things to data. Okay. So here I wrote, and this is something that you typically wouldn't do like in the C class, and that's why I have it here. Justin, this is going to be boring for you, I know. So you're welcome to go. You should look at the others. These are all posted, by the way, on YouTube.
The wiki doesn't seem to have this lecture yet.
The wiki I can't get into. It's I'm right now going back for the RIT. Somehow I'm locked out of being able to log into the wiki.
Okay.
I don't know why. So, but join the class as a Google group.
Yeah.
So join that Google group.
I think I have it.
Okay, and then there's a link to the Dropbox and the videos on YouTube there. Okay.
All right, thanks.
Okay. So here, something you might not be familiar with, functions that take other functions as arguments, and that's really easy to do in Python. So I just wanted to illustrate that and how powerful that is conceptually, what you can do with it. So here, I take this is a function that will take a list and some function, and what it'll do is it'll go through every element of that list. So I'm iterating through every element of that list, and I'll call that function on that element. And if that function returns a true, I'll put that index of that thing on the output. Okay. So basically, so here is an example function, the positive function. So this is given x, it returns if x is greater than 0. Okay. So it's going to return true if the number is above 0, false if it's below 0. Right? Or equal to 0. So that's what that does, right? So then I can say where data is positive, right? And it will tell me all the indices of elements where data is positive. Okay? That's what that does. And I just want you to see this conceptually because actually, a lot of times we use NumPy, it's something very similar construct and things you're doing. So I just wanted you to write it once to just kind of get a feel for what's going on. Okay. And then the idea was to write then I want one of these things that says in range. So this is not just being positive or negative. This is something that I want to be able to get back a function that will tell me it's within a certain range. So I wrote a function that gives me back functions within different ranges. So here's a function in range that then returns a function which tests if things are between any range that are specified. Okay? So something kind of interesting. So you can use this to be able to generate functions for different tasks. Again, this is the reason I'm doing this is to illustrate sort of the power and ease by which you can do this kind of stuff in Python. This really gives you levels of abstractions of concepts that are very powerful. It's not complicated code, but I think the point here is this ability to be able to do this kind of stuff, right? So I made two functions, in range between 0 and 10, and in range between 10 and 20, just arbitrarily I made those, right? And I just was testing them by just calling them what various values. You can see it gives true and false correctly. You can produce yourself at that. And then I can see, and then I can use that fun thing, say where data satisfies F1, that'll give me all the indices, and then I ask for a length, and that'll tell me how many times it was true. Okay? So this will tell me number of entries that pass F1 on to F2. So if you run that, everything was between 0 and 10, this is between 10 and 20, so 0 passed this, and about half of them passed this other one, which was, oh, because I generated between minus 10 and 10. I'm sorry. That's one. Okay. And then you were supposed to go and show that this thing is flat distribution. So what do I mean by this? So I haven't kind of introduced the concept of a histogram. I should have done this earlier, but let's talk about that now. I mean, I guess I have, but and you guys probably know about this. So if I wanted to understand the distribution of ages in this group, I can pick a survey and get all you guys' ages. And then I can, or like, if I want to do curve your exam scores, right? What I would do is I'll make a histogram, where here would be, I don't know, 10, 20, 30, 40, whatever, right? And I'll look at my data, and every time I see somebody with a certain, got at 50 or whatever, at 20 years old, I'll say, okay, it's this band, 30 years old, it's this band, and so on. And I will build some sort of a distribution, right, by looking at the data. In some sense, it's a one-dimensional thing, right? And this is the distribution, the values that I'm looking at, ages, and this is just counting how many people are aged within a particular region, within a particular, group. That's what a histogram is, a one-dimensional histogram. I can make a two-dimensional histogram very simply by doing the same thing, except, I make a grid, and so this may be my x variable, my y variable, and basically every time I see something, I can say, oh, there's one guy here, there's another guy here, oh, I found another one, there's two guys here, there's another guy, two guys, there's three guys here, and I can build a two-dimensional histogram or n-dimensional histogram the same way. Okay? So that's the basic concept of a histogram. So the unique numbers between 0 and 10, minus 10 and 10, and this was supposed to be a flat distribution. What I mean by that is that from minus 10 to 10, if I plot this, it roughly looks straight. Okay? Every single number that you can get is equally probable. So then one way to illustrate that, and it's just an exercise, it wasn't really that important, it's not the best way to do it, is to just pick arbitrary ranges of the same size and show there was the same number of entries in there, approximately. So that's what this code does here. So what it does is that it goes through these ranges. So one thing that we got to be careful with, unfortunately, range doesn't take floating point values, which is really frustrating, and I'll deal with that in a little bit. But other than that, I just check. What I did was I made one of these in-range things, be between this range, and then I just test it in the same way. And then you can plot this out. You can see no matter what range that I have, there is, I get around 25, 27. And this is actually probably Poisson statistics, if I think about it. So it's going to fluctuate because the more and more data I have, the more uniform it's going to look. But in the beginning, there's going to be fluctuations. And so, I can, typically the fluctuations will be the size of the square root of the number. So the fluctuations will be, this is around between 20 and 25-ish, so it's about order of 5. So that should be about 5 of the mean, or 68% of the time, it should be about 5 from the mean, roughly speaking. Okay. So that's an illustration. And then here was just saying, hey, you just did this, let's do it a different way. Let's use something called map. So map is something that will take a function and a list and apply the function to the list and put the results in the output list. Okay? So I map the function in range into this list. So it's just going to give me true, false, true, false, true, false. True is 1, false is 0. And if I do a sum over all those, they'll count how many times it's true. Okay? So another way of doing the same thing we said. I'm trying to do this stuff because I want your head to get around the different ways. I want to start visualizing this data in your head and what it could be and how these operations can get you to the things that you need to know. Or you want to count something, how are different ways of doing it? Okay? And there's not just one way of doing something, there are many, many ways. It is true, though, that some ways will be faster than others. Okay? And so eventually, as we hit those, we'll see. For example, this will be faster than the ways that we did before, because these are internal functions that do the loops. So those the loops here are internal, so it's much faster. Okay? So you want to do things this way. All right, so the last one here was to generate some other data, some other distribution that's not flat. And there's different ways of doing this, but I just wanted to figure out the easy. I just suggested the easiest one. First of all, there was a mistake in my Gaussian. I forgot the minus sign. So the function I wanted you to produce is this thing called the Gaussian.
It was,
Up there. I just scrolled it down. So here, more so far. That was not good. I forgot this minus sign, sorry. Should be minus sign right there. It wouldn't have, if your thing would have rhymed, whatever, it just wouldn't have been showing, the properties it would have been shown would have been. Anyway, so here's the Gaussian function. Make two of them, and so I want to generate this. And the algorithm that I write is a sort of a kind of a silly algorithm. So what I do is, so let's say I have my arbitrary function, and so these are distributions. So I want them to be all positive always. Okay, so we don't have negative probabilities. So these are probability distributions. So we're going to say, let's say my function looks like this. An arbitrary function. That's not the Gaussian function. The Gaussian function just looks like this. Like this. But let's say that's my function f of x. And what I want to do is, I want to draw random numbers, and so that if I get a lot of those random numbers, if I histogram them, it'll look like this. That's the goal of what we're trying to do, okay? So how do I do it? What I'll do is, I'll first pick a random number within the range, so I'll say, okay, here. And then what I want to do is, the probability of something ending up in this particular space, right, should be sort of proportional to the height of this thing. So what I'll just do is then throw a random number between the minimum and maximum of the whole function. So let's say that ends up to be like here, right? And if it's below the value of the function, I'll keep this x. And if it's above it, I won't keep it. Okay? So this, effectively, I'm just throwing a bunch of darts at this picture, right? And some of the darts land inside, and some land outside. And that's really what I'm doing. And I'm throwing through those random numbers, and that's what's going on. And I just keep the ones that land inside. That's the algorithm. If you just count these, this is a way of doing the integral, actually. You think about it, right? So this is a basic Monte Carlo technique. Okay, and I just wanted you guys to practice writing it, just to get the logic. So here's how I did it, and it's not beautiful. I just kind of did it. First of all, so I want to find first of all the minimum maximum of this function, because we didn't specify this, because I can throw in the right range. So I just scan the function. I write a loop, and I just scan the function in steps of dx and keep track of max and min. That's what that logic is doing. Okay, and to do this right, you have to make sure that you have the max is at some really small negative number, and the other one's a really big negative number, a big positive number, such that you can, and this is not foolproof the way I did this one. It's good enough. I'm really just trying to get you guys to get a feeling for what's happening. We'll never write these kind of functions. I'm just trying to get you to visualize when we use the functions, what's happening inside. That's what we're writing. Okay, and then what I do is I'll throw those two random numbers. So I throw one random number, I'll call it x, between the min and max, and then another number, I'm calling it r, between the min and max of the function. So this is this one and that one, right? And then I just see, is my r less than the function at that place? So I'm just making that test. Is this underneath this curve? And if it is, I put it on the output. If it isn't, I'll keep doing this. Where's my big while statement? How do I get n? No, here it is. I do it n times, right? I do this until I have n things in my output list that I know I'm done. So that was it. If you didn't do it, it's fine. If you couldn't get through it, now that I walk through it, keep trying. Okay, what's important here is to get the feeling of how things work and, you know, get the experience. We want you to get up to speed and be able to do stuff like this, but it's okay.
Will this be able to be like referenced later, this answer sheet?
Yeah, I'll put it up, I'll take a snapshot of it, and I'll put it in the Dropbox, or I'll go to Wiki when I get the Wiki working.
Yeah,
Okay?
thank you.
So I'll do that for you guys, that's no problem. And, yeah, I mean, really, it's okay to not get the answer. It's not okay to not try to get the answer, okay? It's the process of failure and trying to figure out how to do things. You'll go through you'll discover all the things you don't know, basically, and then you'll go and learn it to try to figure out the problem. But that's actually the important piece of the process. The right answer eventually may be important, but right now, it's really the process that's more important for me, okay? So it's okay if you don't get the right answer and you couldn't figure it out, but it's not okay if you really didn't put an honest effort into it, okay? And it's okay if you couldn't figure it out, you now go back and you read this, you understand it, and try to write it up yourself or play around with it. That's okay. I don't mind. But I don't want to give you the answer from the beginning either, because I want you to struggle a little bit and see if you can figure it out. All right, that's basically it for that one. So then I want to do just a quick linear algebra sort of thing, and I guess we don't have too much. Oh, no, I should have done that. Oh, that's okay. All right, so we're here in the linear algebra part. Okay. Okay. So let me just get a sense. Everybody's had linear algebra, before that I said probably in high school, right? Everybody saw matrices and vectors and things like that in high school. Is that true? Somebody, if you didn't see it, raise your hand. It's okay.
In high school.
In high school, I didn't see
It's
it.
what you decided here. Okay, so you've seen it now, right? Everybody's seen matrices and vectors, right? Okay. And basically, that's all you have to know. I'm just going to show it to you once, kind of semi-formally, so that you not even formally, but just to make sure we're on the same page. Easy stuff, right? Linear algebra, like when I remember when I first learned about this kind of stuff, they taught us Gaussian elimination. And basically, linear algebra was made to solve systems of equations, right? Systems like this. You get this kind of systems in like when you were doing collision problems in like beginning physics, right? You get all these conservation of momentum in px and py and pz. You write all the momentum before and all the momentum afterwards. You get these things. Or you were doing circuits where you're doing the Kirchhoff's laws. You got these kind of systems of equations, right? So this was just basically realizing that you can abstract that problem away, and that problem can be represented as a matrix. And you can solve that problem with perform operations on a matrix like this. You would do Gaussian elimination with something that looks like this. Or you would write it better, something like this. You say A is this stuff, like this part of the thing. X is my unknown, Y is this. And so I can write that equation with this, right? And then if I could, if it was like linear algebra, I would divide by A and I'll get the answer. We can't divide by A, you have to find something called the inverse of A. So you can write X as the inverse of Y, and then you figure out what inverse is supposed to be and all that stuff, right? That's what linear algebra, the most basic form, okay? Basics, right? So here's a vector, it's just a 1 by n matrix, right? A matrix, an n by n matrix, right? A n by n matrix. Now, when we talk about columns, we're talking about these guys, right? So column. And if I'm going to put indices, actually this works in Python also. When you put colon, it means every index. Okay? So this is a way of saying I mean the columns. And if I want to rows, you say that, you can say this way. It's just a notation. But it's good because it's the notation we use in Python, so it's the same. So that's why I want to use it. Transpose. So basically, if I take the matrix and transpose it, what it does is it flips it around this axis, and basically turns ij into ji. Just flips the indices. That's what a transpose is. If I'm doing things like summation, if I'm adding two matrices, it's just element-wise. So we'll take element 1, 2 of A plus element 1, 2 of B is element 1, 2 of C. Right? It's element-wise adding it through. Okay. Therefore, these guys have to be the same size for this to be defined, right? And then there's the identity, right? And identity basically says if you're long diagonal, you're 1, otherwise 0. The point here is that if you take A and multiply the inverse, it'll give you the identity, right? Or in either way. Or if you take any matrix and times it by this matrix, identity matrix, you'll get back the same matrix. That's what the identity matrix does. Okay? But I didn't tell you what multiplying matrices are. So here are the products. Okay, here are the products. So the most important product that we'll use is the dot product. These are vector operations. There's the inner product, which is the dot product. So you'll see it a lot of times in physics written as x dot y, right? In matrix format, you can write it as x transpose times y. And when I show you the rules for matrix multiplication, that makes sense, right? Basically, what that shows is it represents it takes x, flips it this way, and this is y. And actually, that's what matrix multiplication is. So it's this time you go and rotate it and put it on top of this, and probably multiply it through and add, right? And that's just a way of writing that out. And if I'm going to write it in terms of indices, that's what this is. You just multiply xi plus yi times yi and add them all. Okay. There's actually an outer product, which is you can do as x y transpose. And that still works, except we'll give you a matrix, a funny matrix. We don't use this very much, but I'm just pointing out there's another product you can take. Matrix vector, pretty the same. It's just basically doing this. So what you can see is, if these are columns and I multiply by a vector, what it does is that it gives me something as a linear combination of the columns, right? Because it's taking x1 times that column, so on, right? It's just a way of getting a linear combination of the columns. And in fact, you can look at different ways. You can actually, just by kind of looking at what's happening, just by reorganizing where the sum is effectively, you can look at this product in different ways. Okay? So there's another way of looking at it. Not too important. The matrix multiplication. This one's one that I want to go through a little bit slower. Note that, so you have two matrices with two indices, right? And you sum along the second index of the first one and the first index of the second one, right? So first of all, for this to work, then so let's write this out. If I have A and B, A is at n by m, we'll call it A. This is nb by mb. Then if for this to work, ma has to be equal to nb. Otherwise, I can't do the sum, right? That's one thing. And so it's telling me that ijth component of the output is take I of A, sum over K with K j, basically. That's what that is. A couple of properties of this before I'll show you some more things about it. It's distributive, okay, in these ways. I think this is distributive, this is commutative? No, this is not commutative. Well, it's transitive, what was one of them. But it's not commutative. That's one thing that I'm pointing out. So A times B is not the same as B times A. And in fact, A times B might be possible, B times A might not be possible, depending on dimensions. Okay? And this is just pointing out that A times identity gives you back in. So let's take a look real quick. What I wanted to do was show you just, okay, I'm showing you linear algebra. If I were to code it up, linear algebra, how I would do that, if I can find my appropriate Jupyter notebook. Oh, here it is. Oh, that's not the right one. It must have been, it must have been this one. Is this it? Right. Okay, so here I'm going to do a little bit of basic matrix multiplication, just purely in Python. Okay. So I just by hand made two matrices, two 2x2 matrices, and just simple, right? I can just print them out, and you'll see it. And I want to do now matrix multiply. So it's kind of silly, but I just want to go through it slowly once. Okay. So to do that, first I have to make sure everything works out. So I'm going to get the dimensions of the things. So this is so the way that we have it is the first index is n, the other one's n. So basically